everyone. The third day of the workshop. So we're going to have the second talk by Jason in a minute. I just wanted to announce a change in the schedule. So this afternoon we're going to have Nati twice in a row, and Elhanan's talk on generative model will be tomorrow morning. So this afternoon it's going to be twice Nati. Okay, Jason?
Okay, so in the second part today, I'm going to start talking about how to move towards more algorithmic results rather than geometric or topological in nature. In particular, all of the algorithmic results I present will be about a single algorithm, whether GD or SGD can find solutions of low training error and low test error. So I'll first go over some earlier work on random features and how they're related to neural networks, and then about more recent work on the connection between neural nets and kernel methods called neural tangent kernels and their limitations. Okay, so let's step back a little. Like I've shown you that with the second order stationary points and topological results, second order stationary points are very limited. The only models that have any hope of being where second order stationary points are good is really when you only have a single hidden layer and essentially activations that are quadratic or maybe monomial. And similarly with the topological arguments, it's quite unlikely that you can, just using that, you can prove an algorithmic result. So let's look back to when we do have algorithmic results with just a tiny bit of work. The first one is in a random features model. Essentially, random features is where you fix the hidden layer and only optimize the output layer. So optimization is essentially free there. The optimization of the output layer is a convex problem, and you clearly will get training error 0. And the second area is a local result where you have this sort of polyac gradient domination condition. You can establish this even in over-parametrized results. So it turns out you can kind of combine these two ideas and still say something. Okay, so we're going to try to use these two building blocks. So here's a review of random features. We're going to look at a family of functions defined with respect to integration of a base function phi. There's going to be a measure c of theta, and then so f is going to be the integral of phi c of theta d omega of theta. Omega is just some base measure. For convenience, you can think of theta as uniform on the sphere. So omega is a uniform measure on the sphere. Phi of x theta is perhaps an activation function, and c of theta is some signed measure on the sphere. Okay, so functions of this form, where you put some constraint on the c of theta, induces an RKHS. These functions are, the completion of this family of functions is the same as the RKHS induced by the following kernel. Okay. So how is this related at all to deep learning? Well, the first thing to notice is that if you're very, very wide, you can start replacing sums with integrals, right? So if this is my two-layer network, and I have m going to infinity, then it sort of looks like some integral. I can just sort of, by pattern matching, I just write it as an integral. So if it was finite width, I would just let c of theta be a scaling of the Dirac delta function. And I just put deltas at wherever wj is on the sphere. I normalize, let's use homogeneous activation. So then I normalize the w's and then move all of their norms to the signed measure. Okay. So roughly speaking, when m is very large, anything in this space, anything of that type can be written as a two-layer network. Or in fact, a two-layer network is at least as expressive as this RKHS. Okay. So here's a function from Rahimi and Rek that basically says this. If I have a function f that's written as in this integral form, then I can approximate it with a finite number of bases. So there exists some f hat, which consists of only m of these basis elements, and f hat and f are close. It's roughly something order of 1 over square root m. So not only does it exist, it's Rahimi and Rek gave a simple construction. The construction is you simply sample thetas uniform from the measure omega, and you fit the a's. Yeah.
Barron and Jones. Right?
Oh, this is by Barron Jones, not okay. Sorry. Or Mori, but the RKHS connection is Rahimi Rekt.
What's that?
The connection to RKHS is Rahimi Rekt.
So Barron and Jones was a constructive approximation in Hilbert
Okay.
space, and Barron attributed the idea to Mori, but it wasn't.
Okay, I see.
But I think the proof is different. The proof is different and uses different properties. No? The Barron one uses the Mori.
I don't know, but this theorem is.
I
it's
copied
exactly
this from the Allerton paper, but it's
Okay.
probably, I mean, it's definitely something is from Barron related to this, yeah. Okay. So, right. So functions of, okay. So in other words, you can approximate anything of this integral form with something f hat which is finite and not too big, assuming these norms are bounded here. So it's dense in the RKHS. Okay. So here's a potential proof strategy to show things are learnable via SGD. Okay, so first let's make some assumptions about our target because we need some assumption. A reasonable one is to say that it's approximately in the RKHS induced by the kernel K, or approximable up to some epsilon. Not very important. So F star is in the RKHS and has small RKHS norm. Okay. And the second one is show that SGD learns something as competitive as the best one in the RKHS, norm ball. If you can do these two things, then you've done very well because F star is approximately in H, and you've learned something as well as the best in H. This is it's sort of the agnostic case. Okay, so let's look how to execute step one. Or we don't want to directly assume it's in the RKHS. We kind of want to show that there's a family of polynomial-ish things in the RKHS. So how to do this? Most of the kernels we work with will be inner product kernels, dot product kernels. So I can write rho is just x dot y. It's going to be a function of x dot y. I write this series expansion, summation ci rho I. And then, so I'm going to pretend I'm in one dimension to save notation. And then you can see that you can construct an explicit feature map. Phi of x sub I, you just let it be square root ci x to the power of I. Okay, so that's a feature map. So using this, how do we write down a polynomial in this as a function in this RKHS? So given some polynomial p of x with coefficients pj to the xjth power, we want to write it as linear in phi, right? We want to write it as w dot inner product phi. You can just choose wj to be pj over square root cj. So this is one way I've now written a polynomial as a linear function with respect to the feature map of my RKHS. Okay, so every polynomial, assuming cj's aren't 0, can be written in a way like this. Okay. So now RKHS is dense, but this is when you start need to pay attention to norm, because you may need huge or infinite norm potentially even to start approximating these polynomials if the cj's decay too quickly. So basically what matters here is the RKHS norm is essentially the L2 norm of W. So you don't want the L2 norm of W to explode. So it means if cj's decay too quickly, then the L2 norm will explode and you'll have huge RKHS norm and thus terrible sample complexity. So basically you either need pj's to decay very quickly or cj's to decay very slowly, or some combination of the two. Okay, so this is kind of the ideas of step one, is you can write polynomials and probably other functions too as linear functions in the RKHS.
But Jason, this kernel doesn't have a random feature scheme.
It doesn't have a shift invariant random.
Even if I want to do sampling, I can't approximate. Unless you bound the one norm of the coefficients, I can't.
Yeah, that's correct. Yeah.
So it doesn't align with like the other kernels that you had talked about. I mean, it doesn't have a random feature. You can't just randomly sample to get the approximations that you were talking about earlier.
That's correct. This one.
You won't get that.
Yeah, it should be L1 norm of C.
Yeah.
Yeah, that's correct.
Okay, but to get the representations that you want, you're going to work with the 2 norm.
To get the
So you're
representation.
bounding the 2 norm there, not the 1.
Yes, this one is the 2 norm because I'm looking at the RKHS norm now.
Okay.
Right. Yeah, I'm going to work with 2 norms everywhere.
Okay.
Yeah. Yeah, because it's the RKHS. Okay, where was I? Okay, yeah. So these polynomials can be written as linear in the phi, in some feature map phi. So polynomials, and I think you can make this go through for other simplish functions. Polynomials with fast enough decaying coefficients are going to be in the RKHS. So are analytic functions and things like that, as long as you truncate their coefficient expansion. Okay, so step 2. Remember, step 2 is I want to show that SGD learns something as competitive as the best in the RKHS. Okay, the first thing to realize is things are good if I restrict to 2 layer. This is a convex problem. So I initialize just the W's on the sphere. Then I minimize only over A for some square loss or hinge loss or whatever. Okay, so there's not going to be any optimization issues here. And I'll be competitive. When M is very, very large, it's going to be competitive with the best one in the RKHS. And it's something like this, except I think you're right that it shouldn't be it should be L1,
Yeah.
some L1 measure here. Yeah. Okay. Okay, so let's think about how to optimize 2 layers. I mean, so we kind of already solved the problem with 1 layer, so it's a little bit silly that we're talking about optimizing both layers, but and you can see that this is only really a technical problem because the non-convexity is kind of harmless. I mean, we don't need it to do anything, right? I mean, you can just freeze it. You can set the learning rate to 0 or very small, and all of these things are fine, are going to work. The only thing we need to show is that optimizing WJ doesn't hurt. Okay, so how is this done? The first idea is to just initialize AJ's kind of smallish and the norm of WJ to be order 1. Then when you look at the gradient of WJ, it's very small. Right? The gradient with respect to the other parameter is the product, the gradient with respect to the layer 1 parameter is the product of other layers and so forth. So if I initialize the other layers kind of small, then W's aren't going to move very much. And as you can imagine, when W doesn't move at all, the proof works. So when W's do move, you can bound things. And it's just perturbation at this point. OK. So the W's are not moving very much if I initialize in a way like this. OK. And again, it's just convex with respect to A. It's almost like you're doing gradient descent on a convex problem, except the features are slightly moving, but they're moving such a small amount, you can control this movement. And you're not using this movement to get a better result or anything. OK. So roughly speaking, you need to fix some target function. And yeah, this should be 1 norm, Adam?
Yeah.
Should be 1 norm. OK. All of these should be 1 norms, not the RKHS norm. But this is correct, right? This one, OK, yeah. So the number of random features you need is wrong there. It's not the RKHS norm, but the bound is the RKHS norm.
I I mean, I don't mean to harp on this. I mean, just the issue is you sort of lose the representer theorem when you move to the one mode. So,
Okay.
yeah.
Yes, where was I? Oh yeah. So we're going to initialize so that somehow AJ is smaller in scale than norm of a hidden unit WJ. Then even if you do SGD on both parameter sets, you're going to get something divided by square root m. Okay. So this allows us to optimize both layers. Yeah.
Could you remind me what was the condition on the sigma activation function?
I didn't say. I'm thinking of. You're saying when will this work?
Yes.
Certainly for ReLU, this is going to be fine, I think. I mean, it's pretty broad. I mean, it's going to be standard smoothness type things. Like, yeah. There's nothing very restrictive here, except the Hilbert space changes. And then when the Hilbert space changes, you need to make sure the coefficients don't decay too quickly, and yeah. Okay.
Jason, so can you clarify again how polynomials emerge from any of the discussions?
So roughly.
Or you just have to hard code them somehow?
No. For example, if this is like ReLU,
Yes.
these CIs, okay, you need to do some small trick because the ReLU ones vanish for some coefficients. So you just need to initialize in some asymmetric way that's not quite Gaussian. But you do some small trick. These CIs are all positive, and you lower bound their decay.
Okay.
And then you just construct polynomials like this.
So you're saying that by looking at the expansion of your activation function, you can, if it doesn't decay too fast, you will get enough of an approximation.
Yeah.
To polynomials.
That's right.
And where is this explicit kind of? What are the exact conditions to get?
The L2 norm of this thing is finite, I guess. L2, L1 maybe according to that.
L1 norm for the activation function. And this is which ones will give you ReLU or?
For ReLU, CI is like 1 over I squared, I think. So they're all super they're all going to be, yeah. So it depends on the activation, I guess. Yeah, Ben.
Even if AI is initialized to be small during the optimization, the two layers become balanced, right? Because A is going to get large gradients. So
A is going.
so the top layer is getting more gradients, and
Yes, that's kind of the reason why it doesn't hurt to optimize the hidden layer. Right, because A is getting, like you said, A is getting order 1 gradients, but this one is getting order A gradients.
yeah, but then A become large, and
Yeah, but the risk is
therefore
already low already. The risk is already going to be small enough.
I see.
Yeah. And if it's cross entropy, you probably early stop. Yeah. Or if it's 1 past SGD, there's early stop. Yeah, so it's exactly playing this trade-off between the initialization sizes, plays into the learning rate, and that basically freezes a layer morally. Okay. So what is going on with deeper layers? So Daniele noticed something similar. You simply just define phi to be this giant thing here. So it's x superscript L minus 1 is basically if I initialize all my network weights at random, and then I pass it through the first L minus 1 layers, and that's the output of that. And then that goes into the last hidden layer. So I can think of this now as a random feature, roughly speaking. And that induces some kernel k phi. And similarly, what happens is that the initialization is also so that the amount of movement in W's is sort of bounded relative to the movement in A. So the A's are moving faster in a sense. So the kernel is almost stationary, and the kernel you get is the one induced by this following feature basis. Okay, so to recap, it's if only the A's change, you're going to get a kernel that looks like this. I'll call this kind of the output kernel. It's a little bit unsatisfying is that you're not showing you gain anything from optimizing the W's. Sorry.
So,
Yeah.
sorry, it might be like a stupid question, but the fact that we optimize over A, and that's the main thing, and we bound the optimization over W, does it even mean that we can just not optimize over?
You don't need to optimize W. The bounds do not benefit from optimizing W. In fact, they get hurt a little.
So we can just run SGD over A and like.
Yes. In these papers I'm describing now, where is this? Yeah. In these papers by Danieli and Andoni, that's basically the main idea. Is you bound the movement in the hidden layer, and it shows you don't get hurt by it, at least.
Jason, then if that is the case, then I don't see some role of the depths. Like it seems that any depth doesn't.
The kernel, I didn't describe it because it's kind of complicated. This kernel changes with depth. And you're paying different prices for higher order coefficients when you go deeper. It's not very explicit, but yeah. Okay, so so the non-convexity is all in the W's and it's kind of being fixed. You're not benefiting at all. Here's a slightly more general viewpoint. And now we're starting to move into the regime of neural tangent kernels, which is imagine that all of the parameters are moving roughly the same amount. Is you're still going to have the prediction function, f theta, has a Taylor's, is going to obey a linearization or Taylor's theorem like this thing. The important term is this middle one. Is notice that this term is linear in theta. So imagine this was phi. So this is now phi dot theta minus theta 0. So again, a linear function in theta. Okay. So forget neural nets for a second. Let's think about any nonlinear function. You're going to pretend, let's pretend for now that the first f0 is somewhat negligible. It's roughly 0 or it's order 1. And it won't affect things too much. It's just an offset, albeit a random one. And the important term is this linear term. And then we're also going to later on argue why the second order term is negligible. And OK. So what happens here is you have this linear term, which is doing all the work for you. This is your feature map, and that's your predictor. Theta minus theta naught is your predictor. It turns out that we'll see in a second that this induces this term corresponds to a predictor in the RKHS. Here are some references. The first group, they're grouped by their terminology, roughly speaking. The first group calls this a kernel method because this is like linear in some feature embedding, and when the number of features is large, it concentrates to a kernel. The second group of papers calls this a pseudo network. The idea is similar. They're sort of the pseudo network is sort of it's a function that's linear in the parameters, and the way it's defined is a gradient at the initialization.
Jason?
Yes.
Why do you need the number of features to be large?
Just for the kernel to concentrate. Otherwise, it's like I mean, I always have a kernel. I'll get to it in a second.
Just a low-rank kernel.
Yeah. I'll get to it in a second. If I want to analyze the kernel and say something about the coefficients and whether polynomials are in this space. Okay. Okay. So I'm going to take the kernel viewpoint because it's a little bit cleaner. So f theta is roughly speaking, if you believe me, ignoring the f0 and the second order term, that it's a linear function in knob of f. So my feature representation is phi, which is the gradient with respect to theta of f. So if I have p parameters, this is in p dimensions. Okay, what is good about f hat? Well, it's a linear method. So that means it corresponds to some kernel defined by these inner products. Sorry, this should be Kij and this is nabla Fi, nabla Fj. Okay, so what does this people refer to this in the literature as neural tangent kernel. Because it's tangent because it's a gradient, so it's on the tangent space or whatever. So it's called the neural tangent kernel. Okay, so what do these neural tangent kernels look like? They generically look of the following form. They're going to, I changed notation a little bit here. My network now has L hidden layers, and the output layer is layer L plus 1. There are going to be some linear combination, positive linear combinations of these KLs, and KLs are gradients with respect to that layer of weights. So for example, in the two-layer kernel, I'm going to have two terms in the sum. The neural tangent kernel consists of the first one, this is the one used in Danieli's papers, and also Rahimi and Recht, is that it's defined with the gradient with respect to A. K1 is now the gradient with respect to W. Okay, and you combine them with some linear combination, and I'll briefly say what the linear combination comes from. So is it clear now what the kernel is? Yeah.
Is that left K1 there? Is that a symmetric matrix? Or
they should all be symmetric. They're kernel operators.
Yeah, I couldn't see that from the formulation right there.
If it's not, yeah, it's symmetric, right?
Okay, so sigma prime is a scalar, okay.
Yeah, sigma prime is the derivative of the activation. Yeah. Okay, so you get some family of kernels, this neural tangent kernel thing. Okay. So this family of kernels, in fact, does include the earlier work on kernel methods. The kernel is initialization dependent. Let's just look at the two-layer case. It really matters how the A's and W's are initialized. For example, if the W's are initialized to have variance 1 over D and the A squared are 1 over M, this would be LeCun initialization. And then if you treat M going to infinity but input dimension as fixed, you're going to get K2 only. Because K1 will be vanishingly small. Okay, and then this will get back the kernel used in Danieli's work and Rahimi and Recht. Okay, in the literature more recently, there's a different parametrization. People refer to it as the NTK parametrization. And it's sort of things are scaled like this. Notice what's different is I explicitly pulled out a 1 over square root M when I wrote this parametrization. And now I'm going to initialize the AJs as order 1, the norm of W's as order 1. Input dimension is treated as constant. Then the kernel I get will be K1 plus K2. Okay. And this is what's done in these papers, for example. You can also consider a scaling when the AJs are O of 1 and fixed and only train the W's. Then, of course, you'll only get K1 because you don't ever take the gradient. If A is not trained, you don't take the gradient with respect to A. And that's what's done in this paper by Li and Liang. Okay. And basically, you can get the alpha L's by using different ratios of the width and then using LeCun initialization, or some of the standard initializations and tweaking the ratio of the widths. Or you could get different alphas by layer-wise learning rates. All of these things will get you some different weighting. Okay, so basically NTK is a family of these kernels, and you can view the previous works as looking at the case where you only looked at K2. Or more generally in deep networks, the gradient only with respect to the output layer. For example, this one is for a deep network, but if you look at the gradient only with respect to the output layer, then, this previous result is the NTK where you only optimize the output layer or somehow scale things so the other layers don't matter. Any questions here? Okay. So as Nati asked, this is always a kernel. What is going to infinity? So now I'm going to initialize my layers to be Gaussian, and then when they're Gaussian, I can replace the inner product with respect to an integral and expectation, and I'm going to get some closed forms for K1 and K2, depending on their variances. These guys all have closed forms. This one has like arc cosine, and that has arc sines. You can write it down or assign as homework. But it's not that I don't have the equations here. At least to me, they don't say too much. But they only depend on the angles and the norms. And if the inputs are normalized, they only depend on angles. So they're dot product kernels. Okay. So that's for 2 layers. How do I compute these Ks when you start having many layers, right? Remember, I need to look at the expectation of this guy, where the gradient with respect to a middle layer. And that starts getting a little bit tricky. Luckily, this has been done in a few papers. So basically, the idea is to, okay, so the first idea is that if your widths are all infinitely large, the input feature times W is going to be a Gaussian because central limit theorem. If I multiply it, W times X, and W is very, very big. It's like M by D, and M is like 10 billion. That's going to be a Gaussian process. Okay. The input distribution has the following covariance. And then you can recursively write down the covariance function of this Gaussian process when the width is very large. So it's defined by these 2x2 recursions. You start off with the input covariance, and then you recurse. You define some 2x2 matrix, which is basically the covariance. It's basically the 2x2 covariance of the pre-activation of the previous layer. And then now this is the covariance with respect to the next layer, the pre-activations of the next layer. Okay. What these guys showed is in various different limits, when M, in some informal sense, when M goes to infinity, the notion of limits in all 3 papers is different. You get sigma, this sigma sub L is going to be KL plus 1. It's going to be the kernel with respect to the output layer weights.
Do you know what people did in the 90s, whether they proved this already? Like
So I strongly suspect this half of the slide was proved a long time ago, but not the latter half. Although
what's the last one?
Yeah, let me talk about what the latter half is. Yeah. So this kind of Gaussian process, I think, was, the names that come to mind would be like McKay and Williams. They had Gaussian process papers for neural nets, and Radford Neal had things like this for this first half.
So one hidden layer though.
Oh, was it one? Okay, yeah, one hidden layer. Okay, there you go. So yeah, perhaps this is new too. The second half is definitely was not around more than a year ago, for sure. Okay, so the idea of the, okay, so this tells you how to compute the gradient with respect to the output layer. If you want to do the middle layer, you basically have to use the same Gaussian process reasoning and combine it with the backprop equations. So what you're going to do is, instead of sigma, you're also going to define sigma dot. Sigma dot is basically the covariances of when you pass the pre-activations through the gradient. And that's this matrix here. Notice there's primes everywhere now. So that's the only difference between this and this. And what these papers showed is that K sub L, so L, this is now going to be an intermediate layer, is you simply take the output kernel of the inputs coming in. So you should think of this as X transpose X prime. And then the product of all the earlier gradient kernels. In fact, this looks exactly like the backprop equations. If you just think about the backprop equations, pretend they were scalars and multiply them together, you would get something exactly of this form. Okay. So there is some closed form for all of these things. That's kind of the only thing this slide is saying. And you can go on the computer and implement this kernel. Okay. So now let me talk about why gradient descent will be in fact close to this kernel. Okay, so recall everything we are saying relies on some form of Taylor's theorem, or this linearized network, pseudo-network, sorry. So what needs to happen is that this pseudo-network, the linearized network and the neural net are close if theta minus theta naught null is small. You also certainly need f0 to be roughly order 1. Otherwise, if f0 explodes faster than square root m, then gradient descent cannot stay close to initialization because it needs to cancel it. Okay, so you need to initialize in a way so f0 doesn't blow up. And I'll talk about that in 1 second. Okay, let's first talk about initialization size. So I have my post activations x sub l. This is my my f0. One very important observation from this paper of Li and Liang is that when you initialize AJs to be the 1 over the number of inputs, so LeCun scaling, you get 1 over m, then f0 of x in fact will be order 1. Why is that? Because of the cancellation, right? Because each of these guys is roughly plus minus 1 over root m. You add a bunch of O of 1 things, they scale to root m, and then you divide by root m. So it's an order 1 quantity. So my neural net, although seemingly in the worst case without this randomness, could add up to square root m. The randomness ensures f0 is very small. Okay. So that's from this paper by Li and Liang. It was used later in other papers for the deep case too. So the initialization is a square root m smaller than what it could have been in the worst case. So why does this matter? Because then it's exactly how much you need to move this parameter to forget your initialization. Okay, so here's some heuristic reasoning for why gradient these things will be close. So again, I'm going to look at my Jacobian. What I want to do to solve the Taylor expansion is to, if the kernel method will exactly solve this equation. I have some Jacobian matrix times theta minus theta null equal y minus f0. That's in fact, if I want to solve this equation, I want to get this equal to y. That's what the solution will look like. Okay, so what is the L2 norm squared of theta if I solve the kernel method? So it's simply given by this y minus f0 inner product j transpose j inverse. J transpose j inverse is just the tangent kernel inverse and doesn't depend on m, assuming, again, randomness comes in here. I'm using concentration. Okay. So if m goes to infinity and f0 is order of 1, as done in these papers, the amount you need to move is constant with respect to m. This is the width. The movement required in theta is O of 1. Okay, so when is this prediction going to be valid? Well, you're thinking order of 1 term. Then that means the linearization and the original network may start deviating a lot. Well, to see this, we need to calculate the Hessian of f theta. If you calculate the Hessian of f theta for any size network, you'll roughly find it actually, in fact, is going to 0 as a function of the width. Roughly, it's 1 over square root m. ignoring all things except width. This 1 here suppresses anything that's not width dependent. So let's just look at a two-layer network with NTK parametrization. If you compute the Hessian with respect to Wj, it's 1 over square root m times some stuff. This stuff is order 1 with respect to m. The same thing on the cross term, the Aj Wj Hessian, and the gradient with respect to Aj is 0. It's linear. It's a linear function Aj. Okay, so the curvature vanishes as the width increases. Our prediction function and its linearization, when you have very large width, will, in a constant radius at least, will always agree with the linearization because the Hessian is vanishing. This isn't how the papers write it, but this is, at the end of the day, this is what's happening. The papers do some perturbation bounds on this Hessian j, but really what's happening is the j is not changing because the function is flat. Okay. So what does this mean for the training dynamics? Since you can make the curvature now arbitrarily small, you can now bound the gradient flow dynamics on the linearized network. On one side, I'm doing kernel gradient descent. On the other side, I'm doing gradient descent on the neural net function. And I can bound these two things. So this is gradient descent on the kernel at time t. This is gradient descent on the network at time t. There's something order of the Hessian. And again, ignoring all things width independent, not dependent on the width, it's something like 1 over root m. So by tuning up the width, I make the function flatter, and then these two things are closer and closer.
So are you suggesting that this perturbation of analysis of how j changes is not actually necessary?
Yeah, you can get a shorter proof this way, I think. I'm pretty sure, yeah. Or a different proof. I don't know if it's easier, yeah. But more conceptually clean, yeah.
What nonlinearities can be handled by this?
Oh, that's a good question. Anything smooth can be handled via these informal arguments. One of these papers do, where is it? These, I forget. All three of these papers do non-smooth things, but then the arguments are not this compact. Yeah. Yeah, but I would say the activation is not important here. You can almost get all of the main ideas just by thinking of it as general nonlinear functions, almost. Okay. Okay, so what I've argued now is the kernel gradient descent and the neural network produce similar trajectories, prediction functions, at up to time t. So what have people used this to prove? This has been used to prove that using lacuna initialization that the two-layer network will converge to a global minimizer if you use very, very small step size. That's in these papers here. Similar arguments were used in deep nets, convolutional deep nets, res nets, so forth. Basically, most of the kinds of nets people use. What they basically do is exactly this argument. They try to make these two things close. This numerator has something nasty on top. And then they just make m big enough to cancel the numerator. That's basically the idea. The dependencies are bad. They're at least n squared. Most of them are worse. The best one in the list is n squared.
Jason,
Yeah.
where does the n squared come from? What's the intuitively, what's the numerator
It's
that rises here? Is this
It comes from, morally you want like a spectral norm here, but when you're doing the perturbation, you can't quite get it, the perturbation spectral norm, so you're doing something loose like the Frobenius norm. And then you're picking up dimension where the dimension of the Hessian is n by n. I think that's roughly where it's coming, is you're trying to bound entries or rows or columns of the way J changes, or J transpose J. And instead of some spectral norm thing, you're using something that's not quite the spectral norm. I think that's where it comes. Yeah. I don't think the widths are very important either. I think because they're all worst case for the worst case labels. You can do significantly better as soon as you start assuming things about y. I think. Okay. So this is what people have used this machinery to analyze training error. Again, we can ask the question is, what functions can be efficiently learned if we use these neural tangent kernels? Okay. So again, K is one of our induced kernels. The sample complexity of learning with respect to a kernel is the RKHS norm squared over epsilon squared. So again, we can try to do this trick of writing these functions as, everything as functions linear in the feature map phi. So again, when they're dot product kernels, you can just simply Taylor expand. And then, for example, if you had a monomial of degree k, you can write f of x as some inner product of a vector, ek with phi, and the 1 over ck will enter the coefficient. So if this thing is decaying very quickly, you're paying a lot for the polynomial. If it's decaying very slowly, you pay very little. So the same thing I already talked about before. So that's in the kernel space. You can do something similar for general polynomials, sort of the same argument. You can work out the RKHS norm is going to be aj squared over cj, where aj is the coefficients of the polynomial. And the same ideas work for the multivariate case. So basically, what you can learn is a constant degree polynomial of degree k with sample complexity like 1 over ck. For two-layer networks, you can work out this explicitly. The form of the kernel decays like 1 over j squared. So you're going to need summation aj squared, j squared less than infinity. So the coefficients need to, for this to be finite, the coefficients need to decay faster than geometric for sure. Okay. So people have used essentially this kind of reasoning to start analyzing teacher networks. Here I was talking about polynomials. It's not too far to go from a polynomial to a teacher network with very smooth activations. So now think about sigma, where the activation function is very, very smooth, meaning it has a Maclaurin series and then things decay nicely.
Do you think you're learning in the regression setting with like you actually have some kind of squared loss?
Yeah, I was thinking square loss in my head.
Yeah, square.
Not all those papers are working.
That's correct. Yes, this argument is not directly from any of these papers, so it might be wrong too.
Jason,
Yeah.
can you comment on the sample complexity? So you said that the polynomials with fast enough decay are learnable using these networks in the kernel regime. Can you comment about the sample complexity versus the min-max sample complexity for learning polynomials with fast enough decay?
I don't know what the the minimax rate.
Yes.
I don't know the minimax rate. Sasha. Okay, Sasha doesn't know. No one knows.
Do you have a sense of, is it?
I mean, you're doing as well as kernel ridge regression, which
Well,
seems.
the question is kernel regression with which kernel? Is this like the optimal kernel for these folks for this?
Okay. No, it's not. In fact, I will show you a kernel that's better, I think. I think I have it here.
Yeah, to clarify, I'm not concerned about the 1 over square root of m. I'm concerned about the numerator.
Yeah, I got it. You're concerned about this one.
Yes.
Okay. So how to go from this to teacher networks is quite straightforward, actually. You simply expand the activation in terms of its as a polynomial expansion. And then you just collect terms, whatever. And you get now something that looks like a polynomial. Maybe you need to truncate because it's analytic and not polynomial. Okay, so this is for two-layer networks, and there's a similar recursive argument, similar to what I did in an earlier paper, to make this work for deep networks. Similar idea, you just apply the feature map twice. You recurse the feature map, and then you write a linear thing in the recursion map. Okay, so these papers, Aurora et al. Use this to show for two-layer networks, when this activation is appropriately decaying coefficients, that NTK can learn it. Alan Zhu, Li, and Liang use not this argument. They directly constructed a pseudo network, which is essentially this phi thing I was talking about. So they constructed a pseudo network, and they showed that teacher networks with smooth activations can be written as a pseudo network, meaning morally it's basically phi inner product something theta is this pseudo network instead of this series expansion argument. Cao and Gu, Danieli showed similar things. You can learn some RKHS via a deep network. Oh yeah, and here's the other kernel that Nati was saying. So none of this is really leaving the regime of this kernel defined by Stritteren et al., which is basically this, it's like all polynomial kernel. It's like you just get all the monomials. And then, for example, in that kernel, you would get, you can learn all of these teacher nets too. And you need to recurse it for the deep ones. Okay.
So same question. So do you know how the sample complexity, or like basically it boils down to what's the kernel norm under that simple explicit kernel compared to the complicated kernels you'd get with the tangent kernels from networks?
You can work it out, but I don't know it right now.
Yeah, I don't know right now.
It's computable.
Sure. I mean, the question is, are these methods actually decent methods for learning
polynomials,
or are they really horrible methods that are still finitely relatable?
I'm not sure. Yeah, I'm not sure. I doubt they're the best, but yeah.
Did I understand correctly that when you were talking about not having to move very far from the initialization, that's because you're reaching a point that has that fits it up perfectly, or is this a?
I have that. Yes, for square loss, yes, but I'll discuss this in 1 minute.
Oh, so it wasn't a requirement of the earlier result about not.
For square loss, you run it for all time, and for other losses, you early stop. That's the short answer, but I'll discuss why this is necessary.
So I guess on this slide, I was asking about the teacher network. Is this in the noisy case or the?
None of these papers have noise.
There's no noise. I see.
I imagine if it's additive IID noise, you early stop. It's fine. But I think none of these had noise. I think. Okay. So sort of related to Peter's question is, how does the loss function come in here? So let's look at the case for square loss. For m large enough, some finitely large m0, then f hat t, the linearized network, and ft are close, something divided by root f for all time t. So you can take infinite time. And this is exactly, so this is on the train loss, and this is exactly because you're perfectly fitting the data and the error is going to 0. For logistic loss, you can't quite get this. If you compute it with Lacuna initialization, you're going to get, for all time t, roughly until the logistic loss is a value 1 over m. Okay, so you cannot run for infinite time. For a finite width, you can run for a certain amount of time. If you want to run for longer time, you need the width to be longer for this agreement. But this is interesting in another line of work that Nati will talk about in the afternoon, is for very large times, or we don't know how long, but we know for asymptotically, that it's not going to be a kernel predictor. And so there's some intermediate regime. This result is from when the logistic loss is like 0, basically, super small. And this one was for 1 over m. And then there's some big regime in the middle. We don't quite know what happens. Nati will talk about this, I think, in the afternoon. The other interesting case to think about is when you do SGD, one-pass SGD with fresh data, right? Because now you can't ever stop. And they'll start differing at some point. So for very small time t, if you do SGD on the kernel method and SGD on the network, they'll agree. And then at some point, they'll start differing. And we don't know we don't know what happens to SGD on the network when they start differing. We only know this initial phase. And at some point, they start differing. That's in this paper by May and Montanari and their co-authors. OK. So the kernel regime holds for the train loss with square loss forever, with logistic loss on the training loss for some amount of time until you get to 1 over m. And then you start some intermediate thing. And then eventually, asymptotically, we know what happens. And if it's one-pass SGD, we know for a short amount of time. And then afterwards, we don't know. OK. Let me talk about learning rate. OK, so I didn't mention learning rate at all. And all of those earlier papers set the learning rate at the end. And they set it small enough to get the behavior they want. And the learning rate is very much connected to what parameterization you use. And it's quite subtle. OK, imagine what FA, what I'll call the standard parameterization. It's just a 2-layer network with no pre-multipliers. And FB, which people call the NTK parameterization. Notice I pulled out the 1 over square root m to make it explicit. The standard initialization, LeCun, for example, is W is 1 over D, and A is 1 over m. So notice under this initialization scheme, F at time 0 returns order 1 quantities. Okay. So F0 sub A is going to be order 1. In NTK, since I pull out the scaling here, I need to initialize the A's a little bit differently. Now I'm going to initialize them to be normal 0, 1. Both of these initializations ensure that F0 of x is order 1 and parameterize the same functions. I mean, you just divide the W's by something, right? And it's correct. Yeah.
It's maybe pedantic depending on what you're going to do with it next, but for the NTK initialization, you usually pull out the 1 over D for the W's as well.
Yeah, but I'm treating input dimension as fixed too. Okay. Yeah, that's why I thought about that last night, and I didn't want. Yeah. Okay. So these two things, in fact, will get the same gradient flow path. But when you start talking about gradient descent, they start differing. Let's look at if you do gradient descent on model A with a constant learning rate, that corresponds to using a learning rate that's m times bigger on the NTK parameterization. So basically, what this means is it is important, it was crucial in these NTK proofs that you set the learning rate 1 over m times smaller. All of those papers used eta order 1, which corresponds to an infinitely small learning rate on the standard parameterization. So in practice, if you use wide resonance with bigger and bigger multipliers and you keep your learning rate roughly constant, or at least not decreasing 1 over m, then NTK will not be a good approximation. Okay, so essentially when you have infinite width and you want to use a constant learning rate, you will immediately leave this kernel regime in one step, essentially. Okay, so the inside the parameterization is hiding a learning rate scaling in a sense. Okay. Oh, wow, that's dense. Okay, so now let me start talking about some limitations of these kernel methods. So for example, if my target function is a single ReLU, then you actually need exponentially many random features to approximate this method for the output kernel. This Yehudai and Shamir showed this. So then on the other hand, so what this also means is that you can imagine, I don't know if they directly prove this, but it means if I initialize my model as here, but imagine there were plus minus ones here, then if you used gradient descent, you would have trouble learning this unless you had a ton of random features. However, if we use a different model, and these coefficients are all positive, and then you do gradient descent only on the w's, you're going to converge to w star with only order d samples. So there's somewhat of a gap here, is that as soon as I initialize at random, the evidence points that you need a ton of samples, potentially exponentially. But then if I fix the signs correctly, it's learnable with d samples. So a single ReLU, if you try to learn it with this sort of NTK analysis, you would fail terribly. Another negative result, if I only have dimension to the k number of random features, I can only learn as well as fitting a degree k polynomial. So essentially, if you want to learn better than a polynomial, you need a ton of random, better than a polynomial at degree 5, you need a ton of random features. So it's saying that, it's kind of hinting the RKHS norm is very big or something. Okay. And then here's another negative result. Where's the citation? Okay, it's okay. The citation is my own paper, so no one will get mad. So there's a simple distribution. It's essentially a distribution realizable by 4 ReLUs, constant number of ReLUs. And then if you had less than d squared samples, your 0, 1 test error using any of the kernels, any of the NTKs, no matter what you tune the coefficients, is no better than random guessing. So in some sense, the idea here is that the RKHS inductive bias is very poorly aligned with targets that are sparse in neuron space. For example, in this first example, your target was a 1 sparse thing. In this bottom example, it's a 4 sparse thing. By sparse, I mean you write it f star the target as an integral with respect to a measure. And then this rho is small in L1 norm is what I mean by small. So for example, when you have 1 neuron, it's just a single Dirac delta function. And this other model is 4 delta functions. And roughly speaking, the RKHS inductive bias is the L2 norm of rho. But you're trying to learn a function that's small in L1 norm, and you're paying a ton. So if you could learn with respect to L1 of rho, I'm not saying I know an algorithm that can in polynomial time. If you could, though, your sample complexity is linear in D. And if you use the kernel methods, it's at least D squared. Yeah, Josh.
Can you say a little bit more about the second bullet point? Is that like a statement about like the expressivity or about the like?
No, the linearized kernel expressivity.
Okay.
It's a statement about the expressivity.
So not about the solution you will find, but about the solution space.
Let me get this. It's a statement about if you do SGD on the linearized predictor. And it's saying that will do no better than learning a polynomial of degree k, unless your number of random features is much larger.
Where by learning a polynomial, you're just like estimating the like linear coefficients.
Yeah, monomials. Yeah, monomials up to k. Yeah. Yes. Yeah.
For these low bounds, are there sort of corresponding empirical results that show that this is actually not a problem for whatever, like the same for training, whatever, layered neural network with gradient descent on the same distribution actually does succeed?
Sorry, I didn't.
I'm trying to understand, for these lower bounds, do you have, at least for the first and the third points, are there corresponding sort of empirical results that show that, well, you can learn
we have experiments that do show that SGD does poorly here.
I see.
For this simple distribution, it's basically XOR in 2 dimensions, and then the other dimensions are Gaussian.
So, okay, so in that sense, you could say whatever NTK then does capture well what.
But if you mess around with the learning rates and things, then it's not clear. With your learning rate is tiny, yes. But when the learning rate starts becoming bigger, then it's not so clear that it can learn it.
Maybe I'll rephrase.
Yeah.
So is there an example where a network can provably, well, hopefully provably, or at least convincingly, empirically, learn something that is provably not learnable with a reasonable number of samples using the tangent kernel? Is that
Right. That's. Well, I was asking specifically whether any of those.
right? Particularly any of those or any other.
I'm trying to think. I'm not sure, but I would be pretty surprised if you cannot learn the single ReLU if you start using regularization, I know, for example, if you write this, you can learn it.
I mean, there are distributions on which ReLU will not be learnable. But,
yeah, but for this one where the input is Gaussian and it's realized by a single target, I know.
Okay, that's.
So this is one example where it is learnable by SGD, but it's just the initialization scheme is different. I don't know of one where the initialization scheme matches the NTK, and the only thing you're allowed to vary is like learning rates. Although I would guess there exists.
Jason, take the initialization scheme that works. Calculate the attention curve for that initialization scheme.
Yes.
Is it learnable with that with that kernel?
No.
Okay.
Oh no, but this kernel is like degenerate because of scaling issues. That's the. It's going to add up and it's going to blow up.
Maybe you take this initialization scheme that doesn't.
Yeah.
It has a tangent curve.
Yeah.
It's finite.
Not if m is infinity in this scaling, right?
But you said it's learnable, easily learnable, not with any goes.
Okay, so if you fix it at finite width, the tangent kernel for this will not learn it.
Okay.
Yeah. For this one. Even when this, yeah, it won't learn it.
Even though you will learn it by.
Yeah.
By
SGD will learn this because this tangent kernel doesn't matter if there's the AJs. The AJs get squared, so they're 1. The tangent kernel is the same in this parametrization up to scaling. And the tangent kernel fails for the single ReLU. Yeah. And Maddie's, this paper by Sotano Katabi uses a very different, it uses 1-point convexity, which uses Gaussian of some Gaussian data and some other things. Right. Okay. So how to go beyond NTK? So what follows is not math, it's more opinions than anything else. So of course, an interesting question to ask here is the kernel regime reflecting the success of deep learning? So the NTKs don't do too badly. Like this paper shows they get 77 or 78% on CFAR10. But on the same architectures, when they do SGD, the accuracy was higher. I think it was 80 something, 85 or so. And nothing's changed. They just did SGD versus learned the kernel. They computed the kernel exactly, and then they implemented to and looked at the test accuracy. So there's a gap. It's like 7, 8%, something like that. And so can we close this gap? I mean, and how? So here are some thoughts. The learning rate is definitely important. If you use a small learning rate, then you will see that NTK and the SGD find similar predictors. But in this regime, the test accuracy of both is pretty bad. With the same architecture and the learning rate is better, and that's what I think this Aurora paper did, the test accuracy is higher. It was 7 or 10% higher roughly in that paper. So, and then of course when you're using NTK, you're implicitly enforcing your learning rate to be infinitely small basically, which might hurt learning. So perhaps there's a way where you can set the learning rate initially to be large, move the kernel away from, the current kernels are completely data agnostic, right? They're defined only with respect to random initializations. Once you start doing SGD, these kernels are somehow adapting data. I mean, I can write an equation, but I don't know why they're adapting well. But perhaps you can show you do better. Here's a more concrete example. If you try to solve matrix completion with the following predictor. So the samples now are just the ij observed entries. So there's only d squared possible samples. So your observation pattern is uv transpose the ij entry of it, right? So this is a perfectly valid predictor. If you compute, so now let u and v be Gaussian of size d by m, and where I'm going to take m to go to infinity. So I'm going to do matrix completion with over-parametrized factors for some weird reason. Then what you can ask the question, what will NTK do? It turns out that NTK will simply impute the observed entries. It's going to do the kind of the stupidest thing ever. If there was an observation there in the loss, like a yij, it fills in yij. If there was no term in that loss, it fills in 0. Or sorry, not 0. It just leaves it at the random initialization. And then in these asymptotic calculations, it's kind of suggestive that if you run GD for a very long time, then you will get minimum nuclear norm. The first one is sort of like minimum Frobenius norm to initialization, roughly. So very, very different inductive biases is that you can see in one example already is you kind of rather be in this case. So again, coming back to this logistic loss that Nati's going to talk about, we know that asymptotically, you're going to get a stationary point of this max margin. So max margin with respect to L2 norm of parameters, shown in these two papers here. For even simple models, oh, and notice NTK is generally not a stationary point. NTK solution is not max margin, not a stationary point of this max margin. For even simple models, already L2 regularization on parameters gives interesting inductive biases. For example, for deep linear nets, you get the Schatten 2 over L norm, so closer and closer low rank. If I write a linear model as a Hadamard product of two vectors, that inductive bias becomes an L1 norm. For two-layer ReLU networks, if I do L2 norm on the parameters, it's an L1 norm on the measure. So I'm trying to learn networks that are sparse in neuron space. And for deep ReLU networks, you can't quite write down this as a nice thing like this, but you get some size-free complexity bound. So it's kind of too much to expect that you always get global max margin, except in like matrix completion, matrix sensing. But perhaps you can somehow interpolate between NTK and this global max margin. So one concrete question is, if I initialize at the NTK solution, then what stationary point of this max margin do you go to? Because I know if I run gradient descent on logistic loss, then in the beginning for a very long time, if I initialize very wide, then for a very long time I stay in the kernel regime. So it's basically like I'm going to converge to some stationary point where I'm starting at the NTK solution. So what basin of attraction is the NTK solution in? And I think that's all I have.
Okay, we have time for a couple more questions.
So what's the right learning rate scaling for NTKs?
It's 1 over width smaller. If you want to use a constant learning rate in this parameterization, you need if you use a constant learning rate in NTK, it's eta over m in the standard one. So it's infinitely small learning rate.
Okay, if there is no more question, let's thank Jason again.